So this is a glucose molecule. Glucose is made by plants. You can see that they take CO2 and use sunlight energy to make glucose. This is glucose, C6H12O6. So each blue one is an oxygen, each black one is a carbon, and we have 12 hydrogens that are white. This is your blood sugar, also known as dextrose. And what animals do with this is they convert it back into CO2 and give off energy needed for running our bodies and everything. So just to review this model a little bit, you can see that you have free rotation about single bonds. Here's a double bond, you don't have free rotation. So this oxygen right here has two bonding electron pairs and two non-bonding, but we don't call it regions of electron density because this is not a central atom. Here's a central atom. We have 1, 2, 3 regions of electron density, so it's trigonal and it's planar. So here's a carbon. This is tetrahedral. I got 1, 2, 3, 4 regions of electron density. Bond angle is 109.5. Here's another central atom. This is an oxygen. I got 1, 2, 3, 4 regions of electron density. 2 of them are bonding, so that ends up giving us the bent shape, again 109.5 degrees. So it's pretty much the same all the way through here. So anyway, this video is about molar mass. So what is the mass of this? If we take this all apart, we will get 6 carbons, 12 hydrogens, and 6 oxygens. We'll get this. So here's our 6 carbons at 12.0107 AMU each. Here's our 12 hydrogens and our 6 oxygen atoms. So what we want is to get the mass of all of these, add them all up, and we will get the equivalent of this. So if we look at the periodic table, you'll see that for carbon has an atomic mass of 12.0107. Oxygen 15.994, hydrogen 1.00794. That's where I got these numbers right here. So if we recall from your previous chapters, if I take this number and I'm talking about a single carbon atom, it's going to weigh about 12.0107 atomic mass units. Of course, there is no particular atom that weighs that. Remember, this represents the weighted average of all the carbon isotopes on planet Earth. If I take that same number, I can use it with grams. That means that 1 mole of carbon atoms will weigh 12.0107 grams. And in the previous chapter, I showed you how these are interconvertible. So here's a way to calculate to get the mass of all of these put together. So we have 6 carbon atoms at 12.0107 AMU per atom. It gives us 72 something AMU. 12 hydrogen atoms, that's so many AMU per atom, gives us about 12 AMU. 6 carbon atoms, that's about 16 AMU per atom, gives us about this many AMU. So now I add them all up. I'm not really caring about significant figures right now. So what that means is that one glucose molecule, which is this, representing all these individual atoms, weighs 180.19 AMU, and that is a conversion factor. So I want to point out that everything about a chemical formula is a direct proportion. If I had 2 of these, I would have twice as many of all these other components. If I had 0 of this, I would have 0 of these as well. So now we can use this conversion factor to solve different kinds of problems. So for example, how much does 10 molecules of glucose weigh? Well, 10 molecules at 180.19 AMU per molecule gives us about 1802 AMU. So I'm just using this as a conversion factor. So 2 molecules would be twice that amount, right? This is a direct proportion right here. So how much does 1 mole of glucose molecules weigh? Okay, well, 1 mole is that many molecules, and at that many AMU per molecule, that gives us this many AMU in 1 mole of glucose molecules. Well, in another chapter, we had used this conversion factor, converting AMU, which is relative mass, that is relative to carbon-12 being exactly 12, and converting it into normal mass. So I'm going to take this number right here, the AMU per mole, and convert AMU into grams using this other direct proportion. So I cancel out AMU, what I have left over is grams per mole. So 1 mole of glucose molecules weighs 180.18 grams. It also weighs that many AMU. So notice this is the same number that we previously calculated. If you go back to here, and I round this off to 5 significant figures, I get 180.19. If I go to 4 significant figures, I get 180.2. So we do have rounding off issues because of significant figures, but they're the same number. So here's a couple more conversions we can do. So how many grams of glucose in this many moles? So I start off with that many moles. I need a conversion factor to turn moles into grams, so we already calculated that. So here's our direct proportion. We're using it as a conversion factor. Then how many moles of glucose do we have in that number, but in terms of grams? So I start off with that many grams, and I want to convert it into moles, so I get the conversion factor between grams and mole. So you can see I get that many moles. Another set of calculations that we use the molar mass for is percent composition. So percent composition is in terms of mass. You could use AMU or grams. So for example, calculate the percent oxygen in glucose to 4 significant figures. So we already have that data. So we found that there's 95.9964 AMU of oxygen out of a total in glucose of 180.1870. So this is a ratio. It's also a conversion factor. So we got that many AMU of oxygen out of that many AMU for the whole molecule. That would give us a decimal fraction, so we have to multiply by 100 because percent means parts per 100. So that gives us 53.28%. So that's the same thing as saying that there's 53.28 parts out of every 100 parts. That's what we mean by parts per 100. And notice that we're not talking about oxygen molecules here. That's a total different thing. So we can also use this percent oxygen to calculate other things. So how many grams of oxygen are there in 500 grams of glucose? So the conversion factor here is our percent. So we have to interpret that percent as being a conversion factor. So that means that there's 53.28 grams of oxygen out of every 100 grams of glucose. So that gives us 266 grams of oxygen in that 500 grams of glucose. Another calculation is that we can convert that into moles. So for example, how many moles of oxygen in 500 grams of glucose? So again, we have to go from grams into moles somehow. So to get the grams of oxygen, we had to repeat this measurement. So there's really 266 grams of oxygen. And then I go to the periodic table and I recall that there's that many, there's 15.9994 AMU in one atom, or 15.994 grams in 1 mole of oxygen atoms. Okay. So then I'm taking the grams of oxygen, getting rid of the grams and converting them into moles using this conversion factor, which is a direct proportion. So now I've calculated that in this 500 grams of glucose, there are 16.7 moles of oxygen. Another calculation, how many oxygen atoms in 500 grams of glucose? Well, again, we have to get grams into moles. So I had to repeat all these conversions right here. So first I got the number of moles of oxygen, grams of oxygen, using the percent oxygen. Then I convert that into moles of oxygen. And then we need to convert moles into atoms. So remember that conversion factor is Avogadro's number. 1 mole of anything is 6.022 times 10 to the 23rd things. So in chemistry, those things are going to be atoms, molecules, formula units. So I got this many moles of oxygen. I got to get rid of moles of oxygen, keep atoms of oxygen, and here's my final answer. So that means that in 500 grams of glucose, there are 1 times 10 to the 25th atoms of oxygen. So in this lecture, I just want to point out that every single thing was a direct proportion. Every conversion factor is a direct proportion.